Why do we need calculus? If this is the first time you are approaching the topic of calculus, most of the math that you have studied so far can probably be categorized as being static. Now, I'll admit, it's a little hard to conceptualize what static math is, but bear with me a moment. If we can describe your previously studied types of math as being static, then calculus can be described as being more dynamic. Let's try to wrap our heads around this idea by looking at two problems. So first we have the area problem, and then we have the tangent problem. Let's first explore the area problem. The principles behind calculus go as far back as the ancient Greeks. You see, the Greeks were pretty clever and figured out that they could calculate the area of an irregular polygon simply by dividing it up into triangles, calculating the area of those triangles, and then adding them all up. This algorithm, albeit labor intensive, is very effective in determining the area of shapes with discrete sides and is known as the method of exhaustion. The problem arises when you run into a shape that doesn't have discrete sides, like a circle. But fear not, our enterprising Greeks figured out that they could still use the method of exhaustion to approximate the area. As you can see, if we inscribe the circle with shapes of increasing sides, starting with a triangle, then a square, and so on, we can effectively cover more and more of the area of the circle. Logically, if we take the area of the inscribing polygon, we get a sense of the area of the circle itself. We have now run into a fairly obvious relationship. As the number of sides of our inscribing polygon increases, the closer we get to the true area of the circle. Now let's just try to describe this relationship in mathematical terms. By convention, the number of sides is referred to as the letter n. We can then refer to the area of the inscribing polygon as A, for area, with a subscript n, such that the 12-sided polygon you see on the screen would be described as A subscript 12, or just A12. So the area of our circle, the A in dark blue, is proportional to AN. And remember, every time n gets bigger, we get closer to the actual area of our circle. And it really doesn't matter how many sides we add, we can always add one more, bringing us closer to our answer. So, mathematically speaking, n is approaching infinity. We call this a limit and would say that the area of the circle is the limit of the area of the inscribed polygon. If this type of expression is unfamiliar to you, don't let it confuse you. We will talk about limits in a lot of detail later on. For now, just try to wrap your head around the logic that we have shown that this statement represents. So you may be asking, what about pi? Why didn't those Greeks just use area equals pi r squared? And where did pi come from? Well, pi has actually been around for a very long time, and its history is beyond the scope of this video. But it turns out that a Greek 5th century BC mathematician proved the area equals pi r squared relationship using the method of exhaustion. Now, if you are dreading the idea of exhaustively having to draw polygons every time you want to get the area of a curved shape, then I have some good news for you. Thankfully, if we want to solve these types of problems, we have since discovered other mathematical tools, namely a branch of calculus known as integral calculus. Not only will the study of integral calculus give us a way to accurately calculate the area of a circle, but we can use it to solve a whole host of problems. I've listed a few examples on screen from a calculus textbook. While these are not the most exciting use cases, I hope you are getting excited about the variety of the types of problems that can be tackled using integral calculus. It looks like we're out of time for this video, so continue on to part 2 where we talk about the tangent problem while continuing to answer the question of why we need calculus. If you enjoyed this content, please like and subscribe. Stay curious, and I'll see you in the next video.